Okay, so you can all read the outline of my talk. It's mainly what concerns me is precisely what's in the introduction. It's been called by some people the scandal of quantum mechanics. How the most successful theory we have, the most successful theory in the history of science, which is quantum mechanics, is still a subject of controversy. And, you know, it's been around for over 90 years. And there's this so-called interpretation of quantum mechanics, whatever that means. And I'll say a few words about that. And there's still controversy. What's the wave function? And all that. And I actually agree that it's a scandal. And I would like to get rid of that scandal, okay? And so my talk will be, first I'll give an introduction and kind of motivate the rest of the talk. And it'll start by formulating classical mechanics, which doesn't suffer from that scandal, as I will describe. And I'll give a formulation which is a little more abstract than one usually gets, because that will turn out to be more easily generalizable to quantum mechanics. And then I'll discuss, you know, simple examples. And then I'll discuss the so-called measurement problem. And I'll distinguish microscopic quantum mechanics from macroscopic quantum mechanics. And the same works for classical mechanics, as I'll say. And then I'll see how it all compares with the standard so-called interpretations. And I'll end with what I call the 10 Commandments. Okay. So there's something called, a field called the foundations of quantum mechanics. And that actually comprises 4 different things. If you look at papers on the foundations of quantum mechanics, they are actually 4 different things. The first is the same as the subject of my talk. What is it? That means, how should you formulate the theory? What's the first chapter in which you explain the physical and mathematical, well, we know the mathematical structure. You relate it to physics, and then you go on. That's the formulation of the theory. But under foundations, some people also include the testing of the theory. The question, is it the whole truth with respect to experimental consequence? This talk is entirely about non-relativistic quantum mechanics, because that's kind of the scandal. It's the controversies I'm referring to are not questions that are unknown. They're just fights about what the things mean. And that's usually confined to non-relativistic, the simplest case. The third thing is the so-called interpretations. And that could mean different things. First of all, to justify the assumptions made in this formulation, whatever one's formulation is. Consider alternatives, alternative assumptions. And then consider the implications for philosophy, cognitive science, information theory, what have you. That is so-called interpretations of quantum mechanics. And fourth, what are the physical implications of this formulation? All kinds of, you know, entanglements and quantum information and all kinds of wonderful things. My point of view is that in this talk, I'm only interested in one. And I would like to claim that the foundations of quantum mechanics is only this. That's what I mean by the foundation. Just formulate the theory. That's what the controversy is about. These other questions are really different in the sense, so I do 1. 2 and 4 are not foundations. They're not interpretations. They're simply physics. They're what physicists do. They test the theory. I mean, you're always testing the theory when you do experiments or theories or whatever. And you study the physical implications. That's not foundation. That's just doing physics with the quantum mechanics as formulated in 1. And 3, I consider most of the discussions of 3 are really not central to physics. If you have a proper formulation, then these questions might be interesting, but they're not what I would call foundational. They're just discussions. Okay. And the analog I have is there's no field called foundations of classical mechanics. We know how to formulate classical mechanics. We know how to test it. We know its domain of validity. We don't need a lot of this stuff. And we know all the physical implications, and that's wonderful. And lots of people still work in classical mechanics, fluid dynamics. That's essentially classical mechanics. So classical mechanics is kind of the model for what I would like to do with quantum mechanics. I'd like to make it like classical mechanics. Formulate it and get on with it. Okay? So let me first give you a summary of how to formulate classical mechanics, because I want to model the formulation of quantum mechanics on classical. So as I say, I'm going to do this in a slightly more abstract way than usual. So first of all, consider a closed system, S, of n particles, or n degrees of freedom, each of which has 3 coordinates and 3 momenta. You represent this closed system by objects, mathematical objects, in a Euclidean phase space of 6n dimensions. A state is a point x in phase space, 6n dimensional phase space. And then a property. I want to make a distinction between states and properties. And you'll see how that comes about. A property is just a subset W of points in phase space. For instance, the set of all points for which the energy E is E of the system. The energy E of the system has the value E1. Or, for some reason, okay, or more generally has a value between E1 and E1 plus delta. It doesn't have to be a precise value. That's a property. And then we know that if the state of the system at time x naught, at time t naught is x naught, then the Hamiltonian determines the trajectory of the system for all times, before t naught and after t. What are the predictions of classical mechanics? Well, they can be summarized by saying that a property is either true or false, given the state. So conditional, if you know the state, and if you know it at one time, you know it at all times, given the Hamiltonian. So conditional on the Hamiltonian and the state, you know if the property is true. That's if the point representing the state is in the subspace, and false if it's outside the subspace. And this is the picture I have. This is all of classical mechanics. Here's the state, and there's an infinite number of properties. I've only written down 6 of them, and no, 5 of them. W1, W2, and W3, those are the subspaces. That's what a property is. They're true, and these 2 are false. And all of classical mechanics is determining which physics, and there's an infinite number of properties, but some of them are uninteresting. And you want compact subsets, because those are the ones that are physically interesting. Determining which physically interesting properties are true, given the state, at any time, is the full content of classical mechanics. That's the only predictions of classical mechanics. So let me make a few comments. It's what I call the microscopic theory. And by microscopic, I mean that it applies to any closed system of arbitrary size, but it uses only concepts pertaining to the system itself. It's self-contained. And that's what I mean by microscopic. I don't mean that it's small. It's just that it's a closed system and it's entirely defined by concepts within the system. And I'll contrast that with macroscopic. Note that states are just assumed to exist. And states are never observed. They're never measured. Only properties are observed. And by observing, you just want to know if the property is true or false. So states are just there. You say, let the state be X at a certain time. That determines the trajectory. Microscopic classical mechanics makes no direct reference for how the state got there. You just say, suppose the state is this, the property, nor how the predictions about the truth of the properties might be tested. And nobody complains when you formulate classical mechanics. You just say, well, let the state be this, and the properties are either true or false. And that's microscopic classical mechanics. Now, if you want to know about preparing and testing, you have to have a macroscopic system. A macroscopic system is a special case of a microscopic system. It says that the system under study is in contact with a macroscopic measurement or preparation. So it's only a subsystem of something bigger. And that's macroscopic quantum, macroscopic quantum mechanics. It's not a separate theory, it's just a special case of the microscopic quantum mechanics in which one assumes the existence of measurement and preparation devices. And they're necessarily macroscopic. They're part of a lab. Ultimately, they have to be macroscopic, and they interact with, but external to the system S under study. But microscopic classical mechanics, it's logically complete. If you assume the state, then you determine the truth and falsehood of all physical properties in principle. So, as I say, it's logically complete. And what I want to do is to formulate quantum mechanics in as close analogy as possible to classical mechanics, because I consider classical mechanics to be a well-formulated theory and not subject to any of the controversies, which I will then talk about. Question? No. This is mechanics. But whenever you make a measurement in classical, if you want to determine if your system S is just a single particle, and you want to determine the truth of its position, namely measure where its position is, that means x1 will be true. But you can't measure that unless you somehow have some kind of measuring device. And measuring devices are always macroscopic. At some level, you make a record of where it was at this time. This isn't statistical mechanics. This is pure mechanics. As I say, a single particle, and you want to determine its position. No, S doesn't have to be macroscopic. S can be a single atom or an oscillator. That microscopic means anything. In particular, a single atom, if it obeyed classical mechanics, which it doesn't, would be S. But in order to actually determine the position of that single atom, I have to couple that atom to some measuring device. Yeah, well, it could be either microscopic or macroscopic. I'm just saying it could be either made up of many, many atoms. But this is classical mechanics. It doesn't really matter. The system S, you just ask how many degrees of freedom it has. But you can define it entirely just within the system S. But if you actually want to measure something about S, measure the truth of a property, you have to put it into contact with a physical measuring device and recording device, and that's necessarily macroscopic. Yes? It determines. I'm talking about, you could, but I'm not talking about those kinds of measurements. I'm talking about laboratory measurements. At some level, laboratory measurements record things on a macroscopic scale. Yes. Measurement and preparation are practical things, and that's anthropocentric. I'm talking about how you actually do it in a lab and how you actually prepare. Yes, it is anthropocentric. But my definitions of microscopic classical mechanics are not at all anthropocentric, and I say they're logically complete in themselves. So you're absolutely right. But that's in fact what in practice happens. There are labs, and they prepare systems, and then they measure them. Okay, so that's it. Now, what about quantum mechanics? So here again, I want to define a microscopic theory. There is ladies and gentlemen, no microscopic theory, no respectable microscopic theory. Look at the books. We'll talk about that a little bit, but there is no, because most formulations of quantum mechanics have measurement at the very start. And by measurement, that's a macroscopic. So now I want to say, and that's one of my main messages, that you should be able to define something which is microscopic. That's what made classical mechanics kind of non-controversial. Okay, so let's do it. Microscopic quantum mechanics also defines states and properties like classical mechanics. But these, and this is the essential assumption, that instead of being objects in 6n-dimensional classical phase space, they are objects in 3n-dimensional Hilbert space in general. And n can be anything from 1 to anything. Okay. So, what are they? Well, Hilbert space, we know, contains vectors and operators. Multiply two operators, you get another operator. And the essence of Hilbert space is this quantum incompatibility. The fact that two operators in general do not connect. And that is the circumstances that changes everything, and that makes quantum mechanics that much more, you could say, complicated, but also rich compared to classical mechanics. But let's try to go ahead with the program. Any vector, more precisely array, you can always multiply it by a factor, or the corresponding projector onto that vector, can be selected as the unique state. More generally, a state, a vector is, or its projector are a pure state. More generally, a state is just an operator row, a positive operator if traced 1, and that's called a density. So the state is, in general, a density matrix, and let's just focus on the subclass of density matrices that are one-dimensional and that are just pure states represented by just a vector in Hilbert space. Now, a vector or its projection, here I've defined as a state, but it also can represent a property, because I define a property as a subspace of Hilbert space. Now, it's not just a subset, it's a subspace. It's itself a Hilbert space. So A is a set of vectors. It can be just a single vector here, or it's a subspace of Hilbert space, and to every subspace of Hilbert space, I can associate a projector. If it's one-dimensional, then it's just a vector. But if it's higher dimensional, it can be represented by a projector. So states are density matrices in general, which are not projectors. They have trace 1, but they're not projectors. In other words, a projector is something whose square is equal to itself. In general, states aren't projectors. properties are projectors. For the case of one-dimensional, they're both represented by vectors. So vectors can be either a state or a projector. But the general case is that a state is a density matrix and a property is just some arbitrary projector. Is that clear? Now, the essence of quantum incompatibility, therefore, is the fact that properties are in general mutually incompatible if their projectors don't commute. So you have states, those are density matrices, and then an infinite number of properties. That's all of projectors. Those are all the properties of the system. But properties in general aren't compatible. And it's again a reflection of this fundamental feature of Hilbert space, which is the so-called quantum incompatibility. Two operators in general don't commute. So two projection operators in general don't commute. So properties are in general incompatible. And this, okay, so that's the structure. And now let's ask, what predictions can you make? Well, in classical mechanics, it was very easy. If you had the state, then you could ask, given the state, all properties are either true or false simultaneously. So given the state at one time, you can look at all the properties of the system and divide them into true properties and false properties. Now, if you don't tell me what the state is, then all properties are indeterminate. They're neither true nor false in classical mechanics. They're all indeterminate. In quantum mechanics, can you have states confer truth on properties, as we did in classical? Well, there are two completely non-trivial theorems that govern the answer. And you can imagine, sort of figure, that the answer will be no, you can't have states confer truth on properties. But that is a result of two essential theorems. The first is called the Bell-Coach and Specker theorem, which says that in Hilbert space, no should be consistent truth functions no truth function can be consistently defined to apply to incompatible properties. The quantum incompatibility means there are no truth functions that obey simple consistency that you would want to impose. It follows that obviously the state cannot confer truth on all properties as a result of quantum incompatibility. The most you can hope for is that the state would confer the probability of being true. And this is not an opinion, it's not an assumption. The only assumption I've made is that the systems are represented in Hilbert space and that states and properties can be defined as I said. Okay? So the only real assumption is Hilbert space. And then you just follow your notes. So there isn't simultaneous truth or falsehood for all properties. That's the first theorem. And the second theorem is known as Gleason's theorem, which says that even if you want to confer, probability, there's only one consistent way that a state can define the probability that A is true, and that's via the Born rule. The probability given the state that the property A is true is given by the trace of rho A. Rho is the density matrix, and A with a bracket is the projection operator. That's the Born rule. And so this is, in essence, a derivation of the Born rule. It's saying, if you want the state to do the next best thing to conferring truth on a property, namely to confer the probability of being true, there's only one way to do it, and that's the Born rule. So we're going to assume this Born rule, but it's essentially been derived because any other assumption would be inconsistent. This is forced by the Hilbert space structure and these very non-trivial theorems. I'm not going to go through, it's pretty elementary. Right. However, this, in fact, is a necessary, this defines the probability that A is true, but this is not a consistent probability function. Over all the properties in the Hilbert space. In particular, as I say, the Born rule doesn't define a probability function over the whole space of properties, since it violates this important condition if of properties if two properties are incompatible. So it's a function. The Born rule is a function on any property in the system, but it doesn't define a consistent probability function if your sample space, probability functions are always applied to a sample space. And the sample space cannot be the whole space of all properties, because if you can't apply it to incompatible properties. This is the and the or, which are easy to define. I won't go into the details, but this can be consistently defined. And this Kolmogorov formula would be equal. For consistent probabilities have to satisfy this. This is kind of the probabilistic analog of the distributive law of logic. And the Kolmogorov law is the distributive law of logic applied not to truth. Logic gives the truth and falsehood. This is this formula is kind of the distributive law of logic applied to probabilities. And it's violated for if your sample space is the whole space, if it includes incompatible properties. So we have to do something a little better. We have to restrict the sample space. Every probability function requires a sample space of compatible properties so that they will satisfy. There will be an equals because A and B will be equal. AB will be equal to BA. That's compatible. And that's called a framework, a sample space of compatible properties. What is a framework? It's an exhaustive set of exclusive alternatives. So now I changed from A, B to W, but those are all just properties. So what is a framework? That's the sample space. It's an exhaustive set. It's a set of compatible properties that add up to one. It's exhaustive. It spans the whole Hilbert space, and these properties are exclusive, that means that they're mutually orthogonal. That's a framework, an exhaustive set of exclusive alternatives. Easy. So this is what I call quantum mechanics made easy. Okay? So you have to divide the space of all properties into frameworks of mutually compatible properties. And that's pictured here. So in classical mechanics, if you looked at all properties, given the state, you could tell some of them were true, some of them were false. In quantum mechanics, if you look at the space of all properties, and those are the W's, they have to be classified according to compatibility. So here is one framework, F1. Here is another framework, F2. They can have a property in common, but so WK is, or WK is compatible with these and also compatible with these, but these and these are mutually incompatible. That can happen. So this is the set of frameworks, and the Born rule creates a probability function for each framework. Okay? Within a framework, the properties are all compatible, mutually compatible, but different frameworks are mutually incompatible. Is that clear? Given a state and a framework, the probability function now is no longer just psi, p psi. Psi is just a simple form of rho, it's a pure state. P psi, it's p psi, but conditioned on the particular framework, F1. This then defines a probability function in a space, sample space of mutually compatible properties. That's it. That is the structure of truth. First of all, the state doesn't confer truth in general on properties. It confers the probability of truth, but only conditioned on frameworks. That's the way you generalize classical mechanics to Hilbert space, i.e. to quantum mechanics. Let's look at spin-a-half quickly. Okay, I'm not going to go. You have the Bloch sphere, and basically, let's take the state to be Z plus, and frameworks are just x plus, x minus, or y plus, y minus, or w plus, w minus. So each point on the Bloch sphere and its complement, the orthogonal one, defines a framework. So frameworks just have two vectors in them. And given the state, it's the only property that is compatible with it is this one. And given the state is true, and this one is false. That's a truth function, because it's compatible. But the state is incompatible with all the other properties. But given the state, of course, we know the probability that this one is true, and if this one is, the probability that this one is true is something, and the probability that this one is true is just 1 minus that, according to the Born rule. So this is the simple way of understanding on the Bloch sphere, what you know well, how these, you can understand it in terms of this more general set of definitions. So I've just, okay. I'm not going to go through this because I've basically explained it. This is just a laborious way. So a quantum state defines a multiplicity of mutually incompatible probability functions. All this is what I already explained. So now let's look at conditioning. From the standard Bayesian definition of conditional probabilities, you can ask for the you can condition the state Z plus on the truth of the property X plus. That produces a new state, and it turns out to be X plus. So the state conditioned, given the state and given a framework, all the properties have some probability of being true. If you condition on the state, on the truth of that property, you produce a new state. That you can prove this just from Bayesian so so the transition from psi, which is just the assumed state, to the state conditioned on the truth of a property, namely psi x, illustrates a fundamental principle that if you add to a state the condition that some property is true, you get a new state. You change the physics. That illustrates a fundamental principle, namely that a state conditioned on some information, namely, given a state, and a framework, any property in that framework could be true. But now if you add the information that it's this one that's true, that's a physical condition, and you change the state. That's an illustration of the fundamental principle that information is physical. It changes state. A state with information, namely the truth of one of the properties and the choice of the framework, changes the state. So that says that. Condition on the state on the property X plus changes, adds information to the state, sign thereby changes the state. That, ladies and gentlemen, is what they call the collapse of the wave function. It's just conditioning a state on the truth of a certain property. And then it collapses. And it's the same collapse that occurs in ordinary probability theory. Of all the things that could be true, we know that with some probability, this one is true. So if you condition on the truth of that, then you get something else, and that's collapse. Note that the state psi does not determine the truth, falsehood, or even probability of any property until a framework has been chosen. And that's what I call the breaking of framework symmetry. There are all these frameworks, and they're all somehow equivalent. If you select the framework, condition on the framework, you have to break the framework symmetry. That then creates a probability function. And if you then select an outcome, you collapse the wave function. The way you collapse the wave function is first selecting a framework and then selecting an outcome within that framework. Okay, well, The von Neumann-Luders rule is precisely what I talked about, the collapse of the wave function. You can redefine it more generally. I did it on the Bloch sphere. I won't belabor that. It's what I call this double selection of first a framework and then an outcome within that framework is what I call a microscopic measurement. And similarly, a microscopic state preparation, because that outcome prepares a new state. So it's microscopic because these are all conditions that don't involve anything external. So it's not a measurement in the sense I said before. It's not a physical measurement. It's just a logical operation. Namely, you select a framework, then you select an outcome. That's what I call a microscopic measurement. But it entirely defines the predictions of the theory in a microscopic quantum. And what I say is that all of these operations occur at a single time. There's no dynamics here. This is logical time. Given X, select a framework, and then ask what is, selecting a framework gives a probability function. And once you have a probability function, there's always an outcome. Except you don't know which one, you only know the probability. Then you select a particular outcome. But all that is occurring, is you're saying you first do this, and then you do that. That's occurring in logical time. It can all be done simultaneously in physical time. So now let's ask, what is the measurement problem? So we haven't talked about macroscopic measurements. This is all microscopic. This is all within the system, no matter how small. We did it for a single spin. So since there are no measurements in the traditional sense, no measurement devices, one might think we've avoided the measurement problem, because there are no measurements in the traditional sense, because it's usually phrased in terms of macroscopic. However, one can define what one might call the microscopic measurement problem by noting that this collapse, the von Neumann-Luders rule, as we know, violates the unitary dynamics of the Schrödinger equation. Well, I said this isn't dynamics. There's no time evolution. This is logical time, and there's no unitary dynamics in logical time. That's the so-called measurement problem. Our resolution is to note that this Luders rule, the Neumann-Luders rule, this collapse rule, is a theorem. Everything I've explained about the collapse is theorems about how you define conditioning and selection. It's the only way for the state to confer truth on a property. The direct consequence of the quantum incompatibility of rho and A, of states and properties in general, and the physical nature of information. So the transformation, that's the same as what I've said before. Thus, the microscopic measurement problem is neither about macroscopic measurements, nor is it a problem. It's just a theorem. So you might feel cheated because I've kind of defined it away, but it is the understanding in microscopic quantum mechanics of what is referred to as the measurement problem. But in microscopic quantum mechanics, It just amounts to the difference between logical time and dynamical time. The unitarity is a property of dynamical time. This collapse occurs in logical time. This is what I call quantum mechanics made easy. It's just somehow by definition that if you understand microscopic quantum mechanics, which is all forced on you by the structure of Hilbert space. Okay, so now that was a quick sketch of microscopic quantum mechanics. With all its supposed weirdness and paradox manifested in any closed system. And I've only made one assumption, that everything is represented by Hilbert space. Once you accept that, the rest follows by theorems. There are no assumptions. That's my claim. Now, of course, in order to test the theory or to prepare the quantum state in practice in a lab, you have to put it into contact with macroscopic measurement and preparation devices. This is the domain of macroscopic quantum mechanics, which is, as before, a special case of microscopic quantum mechanics applicable to large systems which have as a subsystem the original system under study, and then it's put into contact with. And the measurement or preparation instruments are assumed to be classical. No, it's a theorem. I mean, it's a theorem if the consequence, you know, the only way you can test it is through macroscopic. You can't test anything in the lab in microscopic quantum. Testing in the lab is macroscopic quantum. And so I'm not even going to go through this because we're all tired and I'm sort of getting to the end. Once microscopic quantum mechanics is accepted, then the macroscopic measurements follow from the usual textbook analysis, which is the von Neumann theory augmented by ideas about decoherence. Decoherence is a macroscopic phenomenon. That is the effect of environments on the measurement instrument and on the system when it's in contact with an external, that's the standard thing. And I won't even go through it because it's textbook stuff. But we already know that through microscopic quantum mechanics, the state confers truth on a property. And it's the true property that it gets entangled with the pointer states of the usual measurement. This is completely standard textbook discussion, and the modern textbooks would involve decoherence. And as I say, I'm not going to go through this. This is the simplest example of the Stern-Gerlach, where the x plus and the x minus are the Stern-Gerlach, by being oriented in the x direction, selected the framework x plus, x minus. So measurement apparatus, macroscopic measurement apparatus, is a mechanism for selecting the microscopic framework. And within that framework, nothing tells you whether it's going to go up or down. intrinsically stochastic. All quantum mechanics tells you is the probability that it'll go up or down because of the absence of truth functions. And that's given by the Born rule, which is here 1/2, 1/2. And this outcome, the truth of this outcome, is shown by the pointer coordinate here. That's of the macroscopic measurement apparatus. And this one is. And so the microscopic theory tells you that this one is true with probability 1/2. This one is true with probability 1/2. Conditioned on this one being true, you get this state, which then is entangled with this pointer, and you read the fact that it went up. And so there's nothing, once you've accepted the microscopic theory, there are no measurement problems, because we've already solved the measurement problem in the microscope. And that just gets coupled to the macroscope. Okay. I've just repeated that. Okay, let me just say a few words about how this compares to so-called interpretations. Well, the so-called Copenhagen or orthodox or textbook quantum mechanics, it's not false. I would consider it the phenomenology of which what I've talked about is kind of the fundamental theory, because it sounds pretty familiar what I said. It's just that the textbook phenomenology says that the meaning of the wave function is that it tells you the probability that there will be some measurement that will give this result. Well, but what's a measurement? Where did that come from? And this says that you can define it all internal to the system, that there is a probability that this property is true. That leads to this result, and so this result is kind of the phenomenology of what I've talked about, but the underlying microscopic physics is as I said. So this is the phenomenology. There's nothing wrong with it, but people, like for instance, famously, John Bell, complained, say, how can you formulate something by basing it on measurement without telling me what a measurement is? And where did this classical thing come from? Well, I say, no. I first define it microscopically, where everything is perfectly well characterized microscopically, and then I show that this follows, but this follows with essentially no further assumptions. Okay. Then there are modern treatments. I like particularly Cochin, who recently, he's the Cochin of the famous theorem, which was essentially 50 years ago, but recently, he's a mathematician. He wrote a paper on the foundations, which is very close to our thing, except that he also used language of measurements. Didn't distinguish between microscopic and macroscopic, and I think it's confusing. But if you just change the language, then it looks pretty much like us. And the same is true for Jeffrey Boob. And John Preskill has a book on quantum information, which, well, the famous lecture notes on his course on quantum information, which are marvelous. And if you look at the first, the introductory chapter, it's all very close to what we did, except he also presents the starting axioms with what's the meaning of the Born rule? Well, it's the probability that a measurement will show this. And if you just change the language to use our language, then it's exactly our theory. So the modern approaches still have this kind of orthodox way of speaking, but it's organized actually to really focus on the Hilbert space. And if you change measurement to what I call microscopic measurement, then it's pretty much what we have done. Many worlds, I'll not say much. It's really geared to cosmology. It's unnecessarily complicated if all you want to do is formulate non-relativistic quantum mechanics, which is not what they want to do, but they've been drawn into thinking and declaring that the only way to understand quantum mechanics is to think about the universe as a whole. I consider it just, as John Bell, extravagant and unnecessary. There's nothing wrong with it, but they just do it in an unnecessarily complicated way. Then there's the consistent or decoherent histories. That has a complicated history itself. Our formulation is a lot like the so-called static histories, which aren't really histories. They're just, but the multi-time histories and consistency condition are also unnecessary. They're not quite as bad as many worlds, but they turn out to be unnecessary. So as I say, these theories are not wrong, but our formulation clarifies the language and eliminates what I call excess baggage of these other microscopic theories. Now, what I call neoclassical theory, Bohmian mechanics or spontaneous collapse. If you look at the literature here, there's a vast group of people who earn their living on foundations of quantum mechanics, especially in philosophy departments, where the dominant point of view is Bohmian mechanics or spontaneous collapse. The less said about it, the better. I consider these, so these are what I call neoclassical. Hilbert space isn't really essential. It's based on classical ideas, and to make quantum mechanics, at least simple quantum mechanics, work, they put in some stochastic assumptions about dynamics. I think, in my view, Pauli's immortal words, that these theories are not even wrong apply. I consider the less said about them, the better. Here are what I call the 10 commandments of quantum mechanics by way of summary. Quantum mechanics doesn't require an interpretation. It requires a formulation, just like classical mechanics. Both classical and quantum are first microscopically for closest of arbitrary size. Quantum mechanics replaces Euclidean space with Hilbert space. Whoops, that got moved. Quantum incompatibility, non-compatibility. Quantum space do not in general confer truth on properties. They confer the probability of truth to subsets called frameworks. Easy. Microscopic measurements consists of one selecting a state, choosing a framework, breaking the framework symmetry, and selecting the outcome that is true with some probability. That's the microscopic measurements. conditioning on the selected true information. The true outcome adds information. This is the microscopic collapse of the wave function. Now, I didn't talk about subsystems and entanglement, but that's the usual discussion of Hilbert space. The secret to solving the measurement problem is recognizing the fact that states aren't observable. Only the truth of properties is observable. And it's observable in the sense that I said. And it occurs in logical time. In this way, the microscopically is fully formulated of closed systems without reference to external apparatus, with no paradox. It's logically complete. And it occurs, the collapse occurs in logical time. Experimental tests are described by the macroscopic theory, which involves classical measurement apparatus. Macroscopic quantum mechanics is an application of a theory. It's not a new principle. The macroscopic Born rules follows from the microscopic with natural assumptions about coherence, which have been tested on models. So it provides a consistency test of the theory, but it is not a new theory. As I said, microscopic quantum mechanics is logically complete. This is just a summary. Now, let me ask about the future of foundations of quantum mechanics. Pierre's quixotic dream is that the foundations of quantum mechanics should rest in peace alongside the foundations of classical. Because there shouldn't be such a field 90 years after it's been formulated. Requiescat in pace. My fond, quixotic dream.
Born rule. If I understand correctly, there's this standard argument due to Hartle and DeWitt, which is that if you take multiple copies of a system and multiple pointers, and you go through the usual von Neumann argument of coupling the pointer to the system, then this wave function on this big multi-dimensional space tends to become very close to that which is predicted by the Born rule. Do you know what I'm referring to? It's just the usual argument using multinomial theorem and using multiple copies of a system and coupling it to many pointers. And I think a question which, something that Steven Weinberg points out, which I think is still, at least I don't know the answer to, is that in this argument that you make about phenomenologically proving the Born rule, which is different from Gleason's theorem, you have to assume a notion of the norm. And you have to assume a notion of convergence. And in that, you use an inner product, so you kind of put in the Born rule. So I was wondering if you have a response to this.
No, it seems to me that once you have declared that one microscopic property of S is true, then the usual measurement says that it's that true property that will couple to the true pointer reading. By Gleason's theorem and these conditioning, you arrive at a true property of the microscopic system. As far as I know, I mean, I've read Hartle's paper and I've read some of Weinberg. They don't put in the results of the analysis, of the microscopic analysis. They try to extract it from the macroscopic analysis. But once you understand, once you accept the microscopic analysis, it seems to me that the measurement theory is much simpler.
No, maybe just to phrase, when you said condition, this thing that you emphasize, that information is physical, so conditioning the outcome or the on the truth of some property, you change the state. But what kind of physical process is that? Meaning, I understand what you meant, but what does that mean physically? That conditioning on the truth of outcome, the state changes. Is that seems to be the, I mean, since that's the analog of the collapse, as you said, is that in what sense is the information acting physically?
Okay. The role of the apparatus is to select a framework. Because I said, before you get a probability function, you have to select a framework. You have to break the framework signature. And there's no way in the microscopic theory to break the framework signature. But once you put the system in contact with a particular measurement instrument, if you point the Stern-Gerlach in the x direction, then that breaks the symmetry and that selects a microscopic framework. Given a microscopic framework and given a state, which has also been prepared, but let's not ask how, you get a probability function, a classical Kolmogorov probability function. Given a probability function, any classical probability function, there's a unique outcome. The physical process by which that unique outcome occurs is intrinsically stochastic. There is no rule other than there will be one outcome and we know the probability of each one. That is just the meaning of probability. So the fact that there is a unique microscopic outcome that is true is, there is no further mechanism. There is no mechanism which says whether it'll be x plus or x minus. Because that would say that there's some way of conferring truth on property. And quantum mechanics says there is no mechanism. The mechanism, the truth of properties, once you have the framework, is intrinsically stochastic. But there's only one outcome for any probability function. So once I've selected the framework, I know there will be one outcome, but I don't know which one it is, and there's no law of physics that determines which one it is. It's intrinsically probabilistic. All I know is for each outcome what the probability is that it will be true. And so if you accepted that there will be one microscopic property that's true, then the coupling to macroscopic devices, it seems to me, is not problematic.
Okay, can I just to follow on that? The boundary between the microscopic and the macroscopic isn't as impermeable, because you could imagine having this experimenter who's doing a Stern-Gerlach experiment and having a larger experimenter who's observing this experimenter. So I think that the problem that Weinberg and Hartle and perhaps others are trying to address is that you now try and consider this entire system by means of unitary evolution, and then try and ask if one can derive the Born rule. And one can almost, it seems, do that, but there does seem to be a gap there. And I think the concern I think that what I'm concerned about is that you're right that there's a theorem in linear algebra, but the link of that theorem with what is empirically observed is what.
I've given you that link. I don't want to analyze the whole thing by using some some kind of unitary dynamics. I've told you that microscopic quantum mechanics already, by theorems, determines that there will be a single outcome. I don't know which one, but I know its probability by the Born rule. And once you condition on the truth of that microscopic outcome, the whole von Neumann, the modern von Neumann theory goes through with no problem. If you want to make life difficult for yourself and not take into account Gleason's theorem, then you get all these problems. But we shouldn't pursue this.
Right.
But maybe we should talk about it.
Well, one thing that I've chatted with Pierre a few times about this, just to demystify things for myself, I always place things in a signal processing context, because I think the stuff that Pierre is talking about is really about mathematical theorems about a logically formulated framework that don't really relate to physics at all, really. I mean, it just says that if you have a certain setup where you take the preconditions that is laid out, Hilbert spaces, states, properties, etc., and probabilities are also well defined. Kolmogorov defines them. Then you are not able to escape certain consequences. Whether that mathematical framework applies to the real world, that's a experimental question. But what he's saying is just properties of the mathematical framework itself. It's not a statement about the world. And that confusion.
The statement about the world is that quantum mechanics is represented by Hilbert space. That's a statement about the world. And it's amply confirmed by 90 years of experimentation.
One shouldn't conflate mathematical consequences. Once you've laid out your mathematical theory, it has its own internal consequences.
That's what I call the microscope.
That's what he is doing. And whether the theory applies to the real world or not, that's at some point, and
but clearly, I think Pierre wants to make a correlate between
no, but the point
right,
is
but
that you cannot physically prove a mathematical theorem. You cannot go in the lab and prove a mathematical theorem. Mathematical theorems are.
But he's assuming that the assumptions like the Hilbert space are satisfied.
Right.
There's only one assumption. The rest.
Right. If you accept Hilbert space, then you're done.
Right.
I also find it puzzling as to why Hilbert spaces should describe the world, but I don't think we have any alternatives, right?
Right. There's no need for an alternative. It's so beautiful.
I mean, I think the question is, suppose you.
But I want to do minimal quantum mechanics, and minimal quantum mechanics doesn't have brains coupled to the system. It has Stern-Gerlachs. And as long as the Stern-Gerlach says that you couple to the pointer of that Stern-Gerlach up, that's good enough. In other words, that's what quantum mechanics. That's the quantum mechanics that one uses. It's just simple measurement instruments that have states, and they're stable states, and you can make records for all the usual reasons. But the point is that you already have solved the microscopic measurement problem. Once you've solved the microscopic measurement problem, coupling it to macroscopics is straightforward, or at least no one has explained to me what the difficulty is. I think we're all tired.